Assalamu alaikum and welcome to lecture number 5. In this lecture we'll be talking about the LTI system as filters, and we'll start the new chapter, that is periodic sampling and frequency domain representation of the sampling and so on, right? So these are the 4 topics that we are going to discuss in this lecture. So based on the frequency response of the LTI system, we observe that it affects the spectrum of the input signal, meaning to say that it passes some of the frequencies, right, and weights some other frequencies and totally removes some other frequencies. Thus, systems can be characterized as filters based on their frequency response. If the system passes all the low frequencies, that is from 0 up to omega c, where omega c is the cutoff frequency, so such a filter is called an low pass filter. So these figures shows the ideal responses of different filters, right? So this is the ideal response for the low pass filter. So you understand, in case of discrete time signals, we have the maximum frequency around pi, and the small or the low frequencies around 0 or 2 pi or integer multiple of 2 pi. So if you look at this figure, it is clear that this is basically response of the low pass filter, because it's passing all the frequencies from 0 up to some maximum limit, which is cutoff frequency, right? Similarly, for the case of the high pass filter, the high pass filters, you understand, high frequencies are around the pi, right? Pi or minus pi or integer multiple of the odd multiples of the pi, that is pi, 3 pi, 5 pi, or minus pi, minus 5 pi, minus 3 pi, minus 5 pi, and so on. So if you look at this response, you can easily tell that basically this is an example of the high pass filter, because it passes all the high frequencies, right, whereas it removes the low frequencies. Another filter we have is the band pass filter. So a band pass filter passes the frequency in of specific band. So for example, we have lower cutoff frequency omega c 1 and higher cutoff frequency omega c2, or upper frequency is omega c2. So a band pass filter will pass all the frequencies between this range of frequencies or this band of frequency. Okay, so that's why it is called a band pass filter. And you understand, responses are replicas, right? So similarly, another type of filter called band stop filter. It is similar to the band pass filter in the sense that it will stop, the band pass filter will pass all the frequencies within specified band. So the band stop filter will stop all the frequency in the specific band. So the low pass filter can be defined as a filter whose response equals to 1 when the frequencies are less than omega c, which is the cutoff frequency. And if this condition is not met, that is the frequency is higher than omega c, they will be stopped or they will be removed. So the response of such a filter will be defined mathematically as defined here. Similarly, for the case of high pass filter, a high pass filter will pass all the frequencies higher than the cutoff frequency. So ideally it will have 1 for frequencies greater than omega c absolute, right, because we are talking about both the negative frequencies and the positive frequencies. And for the smaller value of the frequency, that is the frequencies which are less than omega c, they will be stopped. Similarly, band pass filter will pass the frequencies in a specific band. So it will pass the frequencies, or it will have, the filter will have response equal to 1 when the input frequency is greater than omega 1 and less than omega 2. So omega 1 is the lower cutoff frequency, whereas omega 2 is the upper cutoff frequency. So those frequencies that are higher than omega 2, or those frequencies that are less than omega 1, they will be filtered out. Similarly, for the case of band stop filter, the response will be equal to 1 for 0 for specified band. So all those frequencies that are greater than omega 1 and less than omega 2, they will be stopped, whereas the other frequencies, they will be passed. So they will stop this particular band of frequencies. So it has response equal to this one. The one more filter that most frequently are found is the all pass filter. An all pass filter has a frequency response equals to 1 for all frequencies. That means it will pass all the frequencies. So suppose we have a signal x of n that is composed of desirable part, which is x of d, right? We also call it useful or information signal, right? And undesirable part u of xn, for example, we call it noise. So how can you extract the desirable part from x of n? So if we take the Fourier transform of the input signal x of n, and we find that the desirable part and the undesirable part, they are apart from each other, right? They are at some frequency distance, right? So for example, the desirable part is from here up to omega c, and the undesirable part is from here up to here. Okay, now to extract the desirable part, we should design a filter such that it has response equal to 1 from 0 up to omega c, and it has response equal to 0 from omega c up to pi. So if we design such a filter, right, so if we are in frequency domain, so multiplying the response of this signal with the original signal, we get the desired signal as shown here. Or in time domain, we can say that the filter impulse response is then the inverse Fourier transform of the desired filter response, right? So if we have h of n, then in time domain, you understand, we will convolve the original signal with this impulse response, so it will result into totally removing the undesirable part, and it will result into this signal. So from this slide onwards, we are starting a new chapter. So before starting the new chapter, let's see why we want digital signal processing, right? So to understand why digital signal processing is important, or why it has advantages over the analog signals, let's consider a signal x of t. That's the original signal, and we want to transmit it over a long distance. So you understand, when we transmit a signal, it basically suffers from two things. One thing is the attenuation, that at the received and the signal will be attenuated version of the input signal as shown here. So we represent the attenuation by 1 by g. So the original signal was x of t, and the received signal is x of t divided by g, right? So the one thing is that it will suffer from attenuation. The second thing is that channel will introduce some noise, and we get the corrupted version of the original signal. So that is after adding the noise to the signal, or making the signal corrupt, Okay, so this is the signal. Now traditionally what we do, we just use the amplifier to amplify the input signal so that we can uh, remove the effects of attenuation. So if we use the amplifier, so the received signal is x of t over g plus omega plus sigma of t, which is noise. So after the amplification, we will get x of t, the original signal, plus the gain times the noise signal. So you see, when we use the amplifier, or we amplify the input signal, the noise is also amplified. So you can see that although we have amplitude similar to what we had the signal at the transmit end, but now the noise is also amplified. So for example, our transmission involves very long uh, channel transmission. So after a certain distance, traveling the after the signal travels a certain distance, we use the amplifier, but you see that the signal is also corrupted by the noise. So if we have, for example, uh, at n segments of the uh, transmission, at every segment we introduce the amplifier. So the signal received at the output will be x and t, denoted by x and t, and you understand that at each section, because the noise is also introduced, so it will corrupt the signal very much. And you can see, although waveform looks similar to the what we originally transmitted, but because of the noise added the at the receive, and the signal will not be intelligible. That means you cannot uh, you cannot understand it properly. For example, this is at the original signal was the speech signal, so at receive and it will be very difficult what the speaker was saying. So let's take the example of the discrete time signal. If we have a discrete time signal, okay, and we transmit it, okay, so again it will suffer the same two problems, attenuation and corruption by the noise. Okay, so you understand that we can write the received signal, for example, at this point we can write it, because we are also using the repeater with the gain g. So what will happen, similar to what we had for the analog case, that it will amplify the signal and plus the noise. So for example, this was our original signal. You understand, we represent the signal, a discrete time signal, by voltage levels, right? It has discrete voltage levels. So let's assume that it's a binary signal. That means we are transmitting 0 and 1. So that means -5 volt indicates 1 and +5 volt indicates 0. So at the receive end here, we will get x1 of t, right, amplified by a g plus g times noise signal. Okay, so that is what we received here. So again here it's drawn again the same signal. Okay, so this is the effect of attenuation and noise. So you can clearly observe that the same effects are here what we had for the continuous time case. Okay, so after amplification we get this signal again, because the signal is amplified and also the noise is amplified. But in case of discrete time signals, we are only interested in the sign of it. Okay, so if I take sign of this one, so definitely this one has sign, negative sign, although there are a lot of ripples here, because of the noise. But if I take the sign, so definitely this part has negative sign and this one has positive sign. So if I use the sign, I can quickly recover the original signal from the noise. So from the previous slide, it is clear that discrete time or digital signals, they are uh, not affected by the noise, that thus we can receive the exactly transmitted signal. Whereas in comparison to the continuous time case, the continuous time signals suffer from the noise, and it's very difficult to remove the noise. Thus the discrete times or digital signals, they are easier to process easier to remove the noise from them than their continuous counterparts. So you understand that discrete time signal can exist in nature, such as number of days in a number of days, or the number of balls in 1 over in cricket, uh, etc. We can also obtain the discrete time signals by sampling the continuous time signal. So in this topic, we'll talk about how we obtain the discrete time signal from the continuous time or analog signal. So we use the sampling to convert an analog or continuous time signal into a discrete time signal. So we can say that sampling is a process of converting an analog signal or continuous time signal into a discrete time signal, right? So we represent the continuous time signal by xct, and we represent the discrete time signal by xn. You understand about the notation that for the case of continuous time, independent variable is time, which is continuous, and we use parentheses, whereas for the case of discrete time signals, we use the square bracket, and the independent variable in time domain is n. So this is done by setting a discrete time signal xn equal to uniformly spaced samples of the continuous time signal xat. Here the subscript a denotes the analog. And you understand that sampling is a key process in the analog to digital converter. That is a device that converts an analog signal into digital signal. So the first part is the sampling. So this is the relationship of how we obtain the discrete time sequence. So discrete time sequence x of n equals to continuous time signal sampled at sampling interval t. So xc and t, where n is from -infinity up to infinity, and you understand n will be having integer values. Here t is the sampling period, that after how many samples should you take a sample, or after how much time should you take a sample. The reciprocal of the sampling period is the sampling frequency fs, and you understand that fs equals to 1 over t, and the unit of the sampling frequency is samples per second. So how many samples per second do you obtain? We can also take the another sampling frequency, that we call it a non-linear frequency. This is for linear frequency, and this is the non-linear frequency, also called the angular frequency. So here the relationship between the frequency omega s and the sampling period t is 2 pi by t, or the product of omega s into t equals to 2 pi. Okay, whereas for the linear case, the product of fs times t equals to 1. So this is the block diagram representation of the previous slide. So here we have continuous to discrete converter. This is the XCT, which is a continuous time signal, and this is the equivalent XN. So this is the original signal, for example, that consists of 32 millisecond pulse. Okay, so if we sample it, then we get the samples of this, and you understand these are the samples we obtain by using the sampling period T or using the sampling frequency omega s. So it is understood that sampling is generally not an invertible process, because during sampling you throw away much of the information, right? For example, we have a signal as shown here. So if I sample it, then you can see, for example, I take sample one here, one sample here, right? One here, one here. So this is how we do the sampling, and for example one here. So if you look at this one, we are just getting this information, right? And the here, right, in between these, this information is lost, because at the output we'll have something like this. So that means it's a sampling is not invertible process. Okay, so that means I get one sample here, for example one here, okay, this one, then this one, something here. So the information in between these, right? So at these points we don't have any information now, so that means we are throwing away much of the information. So mathematically we can say that it's a two-stage process. Right, in stage one we have impulse train modulation, and in step 2 conversion of the impulse train into a sequence. Okay, so here we have an impulse train, we multiply the two signals, so you understand, using the shifting property we get samples here, right? And the second one is conversion from the impulse train to a discrete time sequence, because in the impulse train we have still information of the time. So as shown here, so we have original signal represented by these dashed lines, okay, and then we sample it. So we can represent this sampling process by impulse train modulation. You understand, modulation is a process of multiplying the two signal in time domain. Okay, so if I multiply with that one, so I'll get these impulses, which are represented by the arrow. So this is now your XST. Okay, so that contains information like we have at 0, then we have another sample at t, then 2t, 3t, 4t, and so on. Similarly, you have a sample at -t, -2t, and so on, right? And you understand t is the sampling interval or sampling time. Okay, so we have the same signal. If I can take samples like this, right, so if I double the sampling time, that means here I have sampling time equals to t1. If I have sampling time equals to twice of t1, so that means I'll get half of the sample what I have here, right? So I will have sample at 0, then I will have at -t, right, -2t, -3t, and so on and so forth, right? So you understand, because sampling time is double. So for example, previously in this figure we can say that we are taking the sample after 1 second. Okay, so we have sample at 0, we have sample at 1, at 2, at 3, and so on. If I take the double sampling time, that means then I will take the sample at 0, then I will have another sample at 2t, another at 4t, and so on. So in this case here we have sampling time double of this one, so that means here we will have half of the samples as compared to what we have here. So how much should be the sampling time or sampling interval that we'll discuss in detail in the following in the subsequent lecture. Okay, so this is the first step, that you go from continuous time into what we represent xct, and this is the sampled version, so we have xst. Okay, so these are, because they still contain the time information, that is a t, 2t, and so on. So the next step is conversion from impulse train into discrete time sequence. Okay, so if you look at the figure below this one, so here you can see that it doesn't contain any information regarding time, just we have numbers here. Okay, 0 2 and so on, right? So that you understand. Okay, so the xst is a continuous time, while xn is discrete time sequence. Okay, the xst includes the time information, which I have already uh, talked about. Okay, so like if you look at this figure, we have still time information here, but if we look at the figure below this one, that's the bottom figure, so there's no timing information on this figure. Okay, so that's why this one we denote by xst, that is the sampled version of the xct, and this one is xn, and the difference between the two is that xn doesn't contain any information about the time. The second difference between xst and the xn is that the samples of xst are represented as areas of the impulses. Okay, while those of xn are finite numbers. So let's see the effects of sampling. In time domain we sample, so what happens in the frequency domain? So until now we have studied that we have the original signal x of xct, and we have continuous impulse train, which we represent mathematically as summation and running from minus infinity up to infinity, impulse of t minus nt. So this is the impulse train, and we have studied that we multiply the two, so multiplying the two will result into xst, and then converting the uh, uh, removing the time domain information, that is t by n, so we get the frequency, we get the discrete time signal. So multiplying the original continuous time signal by the impulse train, we also call them it modulation. Okay, so we have xst equals to this. Now putting the value of impulse train into this equation, we get equation 2, which is this one. So we have studied the shifting property of the impulse in signal and system when we were representing signal in terms of scaled and shifted impulses. So that means if we have a signal phi of t and we multiply with impulse of t minus t naught, we get phi of t minus t phi of t naught times impulse of t minus t naught, right? So generalizing this, we say x of t equals to summation n running from minus infinity up to infinity xcnt times impulse of t minus t naught, right? So this is the generalization of this one. Okay, so let's convert the equation on the previous slide to frequency domain. So the Fourier continuous time Fourier transform of x of t is represented by x as j omega, xct as xcj omega, and the impulse train as sj omega. So let's start with the impulse train. So because impulse train is, you understand, a periodic signal, so let's find its Fourier transform. To find the Fourier transform, let's first find what are its Fourier series coefficients. So you understand, to find the Fourier series coefficient, we have a generalized equation ak equals to 1 over t integration from t by 2 up to t by 2 minus t by 2 to t by 2 x of t, right? That's the generalized formula for converting the finding the Fourier series coefficient, minus j k omega naught t dt. So because this signal, if we take the period from minus t by 2 up to t, we have impulse of t e power minus j k omega naught t dt, and this signal, it will be equal to 0 for all values of t except when t equals to 0. So when t equals to 0, this will become 1, and this, if you put t here 0, this becomes 1, so 1 into 1 will result into 1. So that means we get the Fourier series coefficient for a periodic train with period equals to t equals to 1 by t. The next thing is how to find the Fourier transform from Fourier series coefficients. So to find the Fourier transform for the given Fourier series coefficient, we say x of j omega equals to, rather we'll write the capital omega because the book follows this notation, so we just say okay, and we write the x of capital omega, right? Capital omega is for the continuous time signal frequency. Okay, so find this one. We have the equation summation k running from 0 k running from minus infinity up to infinity, 2 pi times the ak and times the impulse of omega, in fact capital omega, capital, okay, I write here, right? Okay, so I just write impulse of capital omega minus k omega naught. In this case, omega naught is the sampling frequency. So we say okay, omega naught equals to omega s, right? So this is the equation for finding the Fourier transform given the Fourier series coefficient. So simply multiply the Fourier series coefficient by 2 pi by impulse of omega minus k omega naught times 2, and sum it from minus infinity up to infinity. So that will result into Fourier transform from the Fourier series. Okay, so that means instead of x of j omega, we have the signal s of t, right? The signal s of t. So that means the signal s of t will have the Fourier transform s of j omega, okay, and this is equal to, now the Fourier series coefficient we have found for the this particular case of impulse train, this is equal to 1 by t. So by putting value, we get s of j omega equals to summation k running from minus infinity. Let me write quickly. Okay, so s of j omega equals to, I hope you understand, x of j omega is now your s of j omega because your signal is not x of t. In fact, we represent the signal by s of t, so that's why instead of x of j omega I'll write s of j omega, and the remaining thing is same, okay, because that's your impulse train, that's periodic with period t, so it has Fourier coefficient of 1 by t. So given Fourier coefficients, we can find the Fourier transform, so that's the equation, and by putting value of ak we get this thing. 2 pi by t we can take as common here, so taking the common 2 pi by t we get this is, so this is the Fourier transform for the impulse train. Okay, now knowing the Fourier transform, now if you again see the time domain, so in time domain we have x s t, the sampled version of continuous time signal. This is equal to modulation of the analog signal with the impulse train. Okay, so if I take the Fourier transform of the both sides, so x s t will result into x s j omega, and because in frequency domain the multiplication or modulation becomes the convolution, so and by it's also scaled by a factor of 1 by 2 pi. So that means from this equation we get 1 by 2 pi x c j omega convolved with s of j omega. Okay, now we just found s of j omega equals to, let me, so that's your s of j omega. Okay, now if we convolve x of j omega with s of j omega, because s of j omega is, again you can see that it's a impulse train, so because impulse is the identity of the convolution, so if you convolve any signal with impulse you get the same signal. You understand that, you know that x of t convolve with, rather I should write in frequency domain, because it's same whether you're doing the convolution in time domain or you're doing the convolution in frequency domain. So that means if you have a signal x of j omega, right, so if you have x of j omega convolve with impulse of j omega, right, the capital one, so you get x of j omega, because impulse is identity of the convolution. So if you, whether you are in time domain or in frequency domain, but if there is convolution, so x of j omega convolved with the impulse of j omega will result into x of j omega. If this is scaled, for example, it is scaled by a factor of m, so the resulting signal will be scaled by a factor of m. If this is shifted, for example, by amount of omega naught, so the resulting signal will be shifted by omega naught, right? So if you look at this one, these are the scale, it is scaled by a factor of 2 pi, so this signal will be scaled by a factor of 2 pi. Again, these are the shifted impulses, so this signal will be shifted impulses, so that means this can be written as 1 by 2 pi is already there. Okay, so now this is scaled by a factor of 2 pi, so it will be, again, just, I think from here it's clear that it will be 2 pi and divided by t, and this is the shifting thing, so it will be summation k running from minus infinity up to infinity, and these are the shifted impulses, so the resulting signal, which is x of c j, it will be shifted, so I can write it x of c, right, j, and the this thing will be shifted by omega minus k omega s, right? So the 2 pi cancels with 2 pi, so you get 1 by t, which is here, and then you sum it, again the summation is there, and that's the shifting. Okay, so I think that's all for today. See you in the next lecture. Allah Hafiz.